Welcome to International Biodiverse Law and Policy. This presentation is part two of our three-part series of the economics of biotechnologies. In this presentation, we'll go into more detail to discuss the different ways in which we can convert biomass into different types of biofuels. We can group biomass into four major categories. Wet biomass is biomass with high moisture content, anywhere between 25 to over 50% moisture content. This includes animal manure and other types of wet-derived processing feedstocks. Cellulosic biomass is the largest category of biomass types. It includes any lignocellulosic material ranging from herbaceous to woody biomass. Sugars are biomass that have a high starch content. This includes corn grain, for example, and sugar cane. Oils, as the name implies, are feedstocks that have a high oil content, such as soybeans, algae, types of biomass. Now, each of these different groups can be converted into different types of biofuels via a variety of technologies. For wet biomass, because of the high moisture content, we typically look at something that employs the water in its own process, and those are called hydrothermal processing. The product of hydrothermal processing needs to be refined, and once it's refined, you can generally produce renewable green diesel. With cellulosic biomass, you have a wide range of technologies, mostly thermochemical, that you can employ. This includes gasification and pyrolysis, which can be upgraded into a wide range of fuels, including green diesel, mixed alcohols, methanol, dimethyl ether, and Fischer-Tropsch liquids. Now, lignocellulosic biomass can also be hydrolyzed to remove the sugars from the cellulose and hemicellulose away from the lignin and then sent to the conventional fermentation platform. In that pathway, hydrolyzed lignocellulosic biomass can be upgraded just like conventional sugars into ethanol and butanol. On the other hand, if you have an oily feedstock, you can extract the oils relatively easily and either ferment them into alcohols or esterify them into producing biodiesel, another type of green diesel. Next, we'll take a look at what facilities operating these technologies might look like. The biochemical conversion is a relatively mature and straightforward conversion pathway. You start with biomass, which is brought into a facility. It goes through feedstock handling and pretreatment. In the case of ethanol production, the pretreatment is simple steam and acid to expose the sugars. Those are then sent into the solid liquid separator to remove any dirt and grime that you may not want in your conversion process. Eventually, after conditioning and preparing it for the microbes, you can send it to the saccharification and fermentation tanks, where you're bringing enzymes that can help convert and digest these sugars into alcohol. A byproduct of this process is carbon dioxide, which is often sold to the beverage market or other alternative markets. The alcohol water stream is then sent to distillation. Usually the raw stream has a low concentration of alcohol, and so we use distillation to purify it to over 95 to 99% ethanol. The remaining water is removed through dewatering. It usually contains the lignin residue as well, and so the lignin residue can be sent into a burner or boiler to produce steam and electricity. Other parts of the water can be sent to wastewater treatment, like an anaerobic digester to provide heat. But the final product from this process is ethanol. Although there are several steps in this process, many of these steps are relatively simple in the sense that they're operating at atmospheric conditions and low temperatures. What we'll see in the thermochemical platform is that not only have we increased the complexity of the process, but many of the different steps in this process operate at fairly uh, difficult conditions. They operate at high temperatures and pressures. So we see, starting from the left, the biomass is brought in. We also have some feed preparation. In the case of thermochemical conversion, this includes grinding the biomass, chopping the biomass into fine particle sizes, and ground biomass can be sent to a dryer, which will operate more efficiently on smaller particles than on larger particles. The dried biomass is sent to the reactor. In the case of gasification, which is shown here, you would have the biomass mixing with some hot sand in order to heat up the feedstock to its operating condition, and this could be well above 900 degrees Celsius. When you heat up biomass to that temperature, it will break apart into its constituent molecules. Eventually, you want to produce a rich stream of syngas. Syngas is called this way because it's considered a synthetic natural gas, and it contains mostly carbon dioxide and hydrogen. In the case of converting biomass to syngas, there are a lot of tarry components. These are viscous, petroleum-like liquids that come out with the raw syngas. Those have to be removed in order to not damage the downstream upgrading equipment. And so we use the tar reformer to do this. The tar reformer either scrubs them out or you can combust them as the stream goes through. Once you remove the tar, you have a relatively clean syngas. That syngas can then be compressed in the syngas compression unit. The syngas will still contain some sulfur and carbon dioxide. Because of emission concerns, we often try to remove that sulfur, and more recently, there's growing interest in recovering the carbon dioxide and sequestering it as well. And so there are technologies, amine and LOCAT, here that can help you accomplish those tasks. The clean syngas is then sent into gas compression before being sent to the upgrading technologies. This particular diagram is for the production of mixed alcohols, and so you would send the carbon monoxide and hydrogen to the mixed alcohol synthesis section. And so once it goes through that, it usually takes multiple passes to convert most of the syngas into alcohol. And so you'll have alcohols leaving that unit, and you'll also have unreacted syngas, carbon and smaller molecules. The unreacted gases, eventually we can recover and combust to provide heat for the process. But the liquids that come out of that process, we would then send to our separation technologies, where we remove mostly water and methanol, and the dry alcohol would be distilled to produce mostly ethanol. In the case of mixed alcohol synthesis, we also produce higher molecule or higher sized alcohol chains. This is the mixed C3 plus alcohol shown in the diagram. Those have high value, but unfortunately the United States is not a large market for mixed alcohols. And so in the case of thermochemical conversion, ethanol being the primary product, we see that it's important to find value for these other byproducts coming from the process. As we mentioned earlier, the thermochemical platform has several different pathways from which to convert biomass into different types of biofuels. We already described the pyrolysis, gasification, and hydrothermal platforms in one of our earlier slides. When you convert biomass through these platforms, you're going to produce an intermediate product. In the case of pyrolysis, the product is called biooil, a liquid that resembles crude oil. In the case of gasification, you produce syngas, a natural gas substitute that contains carbon monoxide and hydrogen. In the case of hydrothermal processing, you produce a biocrude, which is similar to biooil, similar to crude oil as well. The difference is that the biocrude has a higher quality than the pyrolysis oil, and so it's often termed with a different name. Biooil and biocrude can be upgraded to gasoline and diesel using cobalt molybdenum catalysts. However, if you don't want to use a traditional refinery approach, you can take the biooil and biocrude and gasify it into syngas. Syngas is attractive because it has a high flexibility to produce a wide range of fuels. You can use Fischer-Tropsch to produce gasoline and diesel as well, or you can use the methanol to gasoline approach to produce gasoline or liquefied petroleum gas. As we saw on the previous slide, you can also use syngas to produce alcohols. And so here's a different view, or a more detailed view, of all the different products you can make with syngas. You can take syngas and produce olefins and waxes via Fischer-Tropsch in addition to the gasoline and diesel. Or you can take the syngas, convert it into methanol, and then upgrade the methanol into ethanol, gasoline, acetic acid, dimethyl ether, formaldehyde. Obviously, you can extract the hydrogen, maybe use it to produce ammonia, which is also transportation fuel. You can use it to produce aldehydes and alcohols. The elements that you see on the graph here on the lines are the catalysts that you can use to produce these different types of products. And so by varying the catalysts and the conditions under which they're operating, you can get a wide range of products from synthetic gas. Just to summarize the different operating conditions of the thermochemical technologies, gasification is generally a high temperature process, so 750 to over 1400 degrees Celsius. It can operate at pressures of 1 atmosphere to over 40 bars. In terms of its gasification, can achieve a fuel yield of about 55 gallons per ton. And this represents a fairly high efficiency of 58%. Fast pyrolysis takes place at a much lower temperature of 450 to 650 degrees Celsius and at atmospheric pressure. Depending on how you operate it, your fuel yield will range between 50 and 90 gallons per ton. It has a relatively lower energy efficiency, but we'll discuss this in more detail in the next slide. Hydrothermal processing can operate at a wider range of temperatures depending on what products you're trying to produce, and typically operates at higher pressure than fast pyrolysis, but lower than gasification. So to give you a comparison of the energy efficiencies of the various technologies that we've talked about, we're going to refer to a study by Robert Annex and colleagues, where we looked at the efficiencies of pyrolysis, gasification, and cellulosic biochemical ethanol. What you can see here, pyrolysis, when you include the energy value of all the different byproducts, such as its carbon biochar byproduct, you'll find that it can have an efficiency of 77%. Most of this, as you would desire, is found in the liquid product. However, we have to discount the energy brought in from an external source, such as natural gas. But if you look at just the pyrolysis itself, close to 40-some% of the energy ends up in the liquid fuel, and then you have significant amounts of energy in the char and the fuel gas. If you move on to gasification, you can see that efficiency is between 42 and 53%, and most of the energy value is contained in the gasoline and diesel products. With the biochemical ethanol, we have a lower efficiency, about 44%, and most of this is due to the fact that the lignin content of the biomass is not necessarily converted into liquid products. Instead, it's converted into electricity. On an economic comparison basis, you can see here the biochemical platform. This is the lignocellulosic biochemical platform, not the corn grain platform. And so the capital cost for that technology is a little bit higher than the conventional corn grain ethanol. In our analysis, we found that it was close to $400 million for a 2,000 ton per day facility. For a similar size facility, your gasification plant will be much more expensive than the biochemical approach, and we anticipate that the pyrolysis platform would be the lowest cost option among the three of these. This translates into a much lower cost estimate for the pyrolysis platform compared to the gasification and biochemical approach. Now, for all these technologies, in 2010, we anticipated that the biofuel price would range between $2 and $5 per gallon. These are costs for mature implementations of the technologies. And in later on slides, we'll talk about what are the challenges to meeting some of these prices, which appear to be competitive in the current market. All right. We grouped the biomass into four main types, and each of these types of biomass can be upgraded to different types of fuels. The biochemical and thermochemical pathways can employ a variety of complex processes to transform biomass into heat power fuels and other types of byproducts. The thermochemical platform in particular has a wide range of flexibility in terms of the various pathways that can be utilized to produce different types of products.